Everyone, my name is Rudolf Römer. I'm one of the co-organizers together with Francesca Rondina, whom you see with a lovely green background from the Institute, and of course Andreas Honecker from Cergy-Paris. Welcome to all of you. We have a very tight program. Please let me remind all speakers to keep in time. I, as chairman this morning, have the power to mute you, which I will make vicious use of. When you're listening and not presenting, please turn your audio off. But like I said, video is probably nice as long as we don't have any bandwidth issues. And when you want to ask a question, please post it in the chat window. And I think that's good enough for all of us. Let's kick off. And I'm delighted to start with a presentation from Professor Yidong Chong from Singapore, who's going to talk to us about band topology in non-Hermitian systems.
Thank you, Mr. Chairman. Now, with this kind of seminar where it's not exactly a non-specialist audience, but it's not exactly a topical audience of topical specialists either, it's always hard to calibrate the degree of difficulty of the talk. So I try to do my best, but if any of this is kind of confusing to you, please don't hesitate to speak up. Just directly pipe up, okay, and I'll try to go a bit slower. So today I'd like to talk to you about the theoretical work that we have been doing in our group about physics of non-Hermitian systems and how to integrate them with this other topic of band topology. So let me just take this one at a time. So non-Hermitian physics is kind of a topic of growing interest in the past few years. The basic idea starts from really undergraduate physics, where as undergraduates, we learn that when you deal with quantum mechanics and you use Hamiltonians, the Hamiltonian has to be Hermitian. Later on, maybe some of us learned that these Hamiltonian formulations are not necessarily restricted to quantum mechanics by various kind of formal mathematical mappings. Various other kinds of physical systems, including classical electromagnetism, mechanical systems, and so forth, can also be cast in the form of this Schrödinger equation. As I said before, the Hamiltonian here has to be made Hermitian because we want the eigenvalues to be real. It also has other mathematical consequences. For example, the eigenstates are orthogonal. And as a consequence of all this, under time evolution, probability is conserved. Now, of course, this is a strictly mathematical requirement, and as mathematicians, you can ask what happens if I make it non-Hermitian. However, there's also a physical meaning. Roughly speaking, Hermiticity refers to energy conservation or conservation of probability, things like this. So by making the Hamiltonian non-Hermitian, you are applying this to physical systems in which there is dissipation or loss or amplification of gain. Basically, the magnitude of the wave function absolute squared increases or decreases with time. Traditionally, this is regarded as kind of a weak or perturbative feature. For example, you have a weakly damped system. You just describe it as a Hermitian system and you add some kind of non-Hermitian perturbation to it. However, in recent years, people have realized that non-Hermitian physics can have qualitatively different phenomena associated with them. So one example of this is the topic of PT symmetry, which began with the work of Carl Bender. And the basic idea is that if you have a non-Hermitian Hamiltonian that obeys something like this, it commutes with a operator PT, which is composed of a operator P, which is a parity operator, and an operator T, which is the antilinear time reversal operator. Then such a system is non-Hermitian, but it has some other features that are intriguingly similar and other features that are intriguingly different from standard Hermitian systems. So for example, it can exhibit a kind of spontaneous symmetry breaking, a non-Hermitian version of a spontaneous symmetry breaking phenomenon between a PT unbroken phase, which has real eigenvalues, and this happens if the PT operator maps an eigenstate psi onto itself, Then by application of the PT symmetry condition, you can show that the eigenvalue E has to be equal to E star. Or if PT does not map an eigenstate to itself, but it maps an eigenstate psi1 to another state psi2, then by applying the same commutation relation, you can show that psi2 is also an eigenstate of H with an eigenvalue that is the complex conjugate of the original eigenvalue. So these are two logically exclusive or logically complete cases. And so then you can have a kind of a spontaneous breaking between the case where the eigenvalues are purely real as they are in Hermitian systems or when they occur in complex conjugate pairs. Now this was originally a mathematical curiosity, but slightly over 10 years ago, the group of Dimitri Christodoulidis pointed out that you can realize this in a real system, not a quantum mechanical system per se, but something involving classical optics. And the basic idea is that classical electromagnetism can map onto things like wave equations and other things that can be described by Schrödinger equation-like formalisms. And in that context, you can formulate PT symmetry, which has a very simple form. Basically, if the refractive index has a real and an imaginary part, the ordinary real part is just what we think of as the standard refractive index, but the imaginary part describes the rate of amplification or loss. Then by engineering a system with the appropriate amounts of gain or loss, or rather gain and loss, such that n of x is n of minus x star. That means when you reflect across x, you also take the complex conjugate to take gain to loss and loss to gain. Then it's possible to realize this PT symmetry breaking phenomenon, and this has various consequences for the evolution of optical beams in various sorts of systems. So this led to a kind of explosion of theoretical and experimental research exploring how to realize PT symmetry in various sorts of optical systems. Now, non-Hermitian physics is not only restricted to PT symmetry. There's also this other interesting phenomenon of exceptional points. So briefly, degeneracies in Hermitian systems, as we all know, are places where two eigenstates come to the same eigenvalue. Okay, this is what mathematicians call a diabolic point. And because in Hermitian systems, all eigenstates have to be orthogonal, the two states that participate at a diabolic point remain orthogonal, even though they have the same eigenvalue. However, what can happen in non-Hermitian physics and tends to happen is that when degeneracies occur, this tend to be a different kind of degeneracy called an exceptional point or EP. And typically, the two eigenstates are non-orthogonal, and in fact, they coalesce at the exceptional point. And this is basically a reflection of the fact that eigenstates in non-Hermitian systems are not constrained to be orthogonal. Exceptional points have been explored for, again, they can be realized in classical electromagnetism and various other systems, and they have been recently explored for things like optical mode conversion, sensing, and so forth. So much for non-Hermitian physics. Now, next, I want to very briefly talk about band topology. So let's move out of Hermitian physics and go back to the Hermitian case. We know that when a system is periodic, for example, when we are talking about atoms in crystalline solids, the energy spectra form band structures. And the most elementary kind of thing you can ask about a band structure is what its topology is. These topological properties have really come to prominence starting from the 1980s, basically from Bloch's theorem and the definition of the Bloch wave function. From this Bloch wave function U, you can define the topology of the band N by first defining this thing called the Berry connection, which is a real vector defined as the k-space derivative of U, and then you take the inner product of this with U itself. And from that, you can define things like Chern numbers or various other more complicated topological invariants that are used to classify band structures. And condensed matter physicists have gotten a lot of leverage out of this. For example, if two band structures are topologically inequivalent, there's this thing called the bulk H correspondence principle, which tells you that if you take these two materials and you put them next to each other, there have to be these surface states that flow, they are confined to the interface between the two materials. And these are so-called topologically protected states, meaning that you can perturb the systems and these states still exist because they are protected by the fact that the two band structures on either side of the interface are topologically inequivalent. So the diabolic points, which I mentioned before, the points where two eigenstates become degenerate in a band structure, play a kind of like the role of an elementary building block for generating non-trivial band topology. So roughly speaking, you can start with something like called a conventional insulator, where the topological invariants are all all zero, and then the bands touch, you form a diabolic point. And then when you tune the system further, and then the band gap opens, and then you can create in this way a topological insulator where the bands are topologically inequivalent from what they were before. And there are various sorts of diabolic points that condensed matter physicists have played with, including the famous Dirac point, which are 2 by 2 Hamiltonians that are described by this sigma x kx and sigma y ky, where k is the quasi-momentum and sigma are the Pauli matrices. And these things have diabolic points at k equal to 0. Now, then what happens when you put together non-hermiticity and band topology? It turns out that things start to break down. Bloch's theorem still holds if so long as the system is periodic, still holds even if it's non-Hermitian. However, there's an interesting theoretical problem which you see when you try to apply standard definitions of band topology to the non-Hermitian case. This is a bit too technical to explain, but one way of thinking about it is the Berry connection, which I mentioned before, is no longer real. Okay, if you think about it, another way is the so-called Berry phase. It's no longer real when you have amplification or dissipation in the system, and this kind of screws up your trying to use this thing to define things like Chern numbers and other sorts of band invariants. So then there's been a lot of kind of a cottage industry over the past few years about how to reformulate the concept of band topology to cover the case where the Hamiltonians are no longer Hermitian. For example, there's this nice review article that was posted late last year. So there's this kind of aspect that's interesting to explore, but also things like other interesting physical consequences of putting together things that are topologically non-trivial, and then you add non-hermiticity to them, and how to observe them. So this is something that in my group we have kind of been playing around for quite a few years, and we've explored from various aspects of it. So unfortunately, because I don't want to drag this talk to drag, so I will kind of skip past some of this stuff that we have explored in the past few years and kind of go into maybe one of the most recent papers. Okay, I'll zero in on one particular aspect of this non-Hermitian band topology that we have started exploring over the past year. And the idea is the following. So we know from the work of Bender that PT symmetry allows a non-Hermitian Hamiltonian to express real energy eigenvalues, and this has led to lots of interesting consequences. However, in a PT symmetric system, the eigenvalues are real, but the eigenstates are still non-orthogonal. Okay, and this is fundamentally the problem that with trying to apply band topology to this. And could there be not PT symmetry, but some other form of non-Hermitian symmetry that can be used to stabilize this eigenstate orthogonality property, which was crucial for Hermitian Hamiltonians? And then what would be the consequences for it? Could this be used to try to formulate topological phenomena in non-Hermitian lattices. So our answer to this is in the affirmative. So there is a set of symmetries that we came up with that's more complicated than PT symmetry, but does stabilize eigenstate orthogonality. So I'll briefly kind of go into the math a little bit. So let us define this 4x4 matrices as follows: 0, sigma mu 0, where sigma mu's are the extended Pauli matrices, sigma 0 being the identity matrix. Then we apply the two, not just one, but two non-Hermitian symmetries. One of them is pseudo-hermiticity, which is sigma 0 h sigma 0 equals h dagger. And this can be shown to imply that the eigenvalues form complex conjugate pairs. The second is what's called an anti-PT symmetry, which is the anti-commutation of H with this particular combination, sigma 3, sigma 1, T, where T is the familiar time reversal symmetry operator. This is very much like PT symmetry, except normal PT symmetry would be a commutator rather than anti-commutator. This is why this is called an anti-PT symmetry. And it turns out that this property implies that the eigenvectors must form orthogonal pairs. Okay, if a psi is an eigenstate, then the combination sigma 1, sigma 3, T psi is also an eigenstate that is orthogonal to psi. This is by a mathematical identity. So when both of these symmetries are present, there are two logically complete cases. One where the eigenstates form this rectangular pattern in the complex plane, where the anti-PT symmetry maps, for example, this eigenvalue to that one. This is by minus e to minus e star. And the pseudo-hermiticity maps this guy to that guy. Or you can have a state that maps to itself under pseudo-hermiticity. And then anti-PT symmetry maps this guy to its negative value. And this guy are orthogonal. Okay, so then the question is, okay, so this is a fairly abstract mathematical symmetries, and the question is it possible to realize this? And it turns out that it is much simpler than you might have feared, that we came out with a fairly simple tight binding lattice to realize this, involving a honeycomb and adding various staggered real and imaginary detunings to the on-site terms. When you do this, then you find that the resulting band structure is purely real at most parts of K-space. And then despite the system being non-Hermitian, this is the parameter gamma describing the amount of gain and loss in the system, you still have Dirac cones. These are the Dirac cones right here. And you can show formally that the band structure reduces to a two-dimensional Dirac equation. Then there are lots of interesting consequences for this. For example, you can create a topological transition to convert this system between a Chern insulator and a topological insulator and conventional insulator through a topological transition. However, normal topological transitions in Hermitian systems are induced by tuning some kind of Hermitian parameter, such as the mass of the lattice sites. However, this topological transition occurs in a non-Hermitian system, and it can be induced by tuning a non-Hermitian parameter, the amount of gain and loss in the system. And you can create this kind of topological H states that are amplifying or dissipative. They are very much like the topological H states you see in topological insulators.
3-minute warning.
I'm wrapping up. But it's purely induced by gain and loss. So you can also do something else that's very interesting as well. As I mentioned before, the band structure of this system has Dirac points here, okay, as shown here. And the Dirac points, the location in K-space depends on the gain and loss. So what you can do is you can create a lattice where the amount of gain loss varies inhomogeneously. And then, roughly speaking, the K-space positions of the Dirac points in one part of the lattice and another part of the lattice is different. And this is precisely what a magnetic field does. So by applying amplification and dissipation to a system, you can mimic the properties of a magnetic field. This has been observed before in the context of straining a lattice, which is a purely Hermitian phenomenon. So if you take a Hermitian system and you strain it in a particular way, you can create the effects of a magnetic field, including the production of flat bands called Landau levels. And here we show that you can do it entirely in a non-Hermitian system by using this gain and loss. And again, these two topological properties really come from the fact that we are manipulating a Dirac equation in a non-Hermitian system. A direct equation, not a exceptional point. So that's the conclusion of my talk, and basically we have kind of covered the idea of non-Hermitian systems and how normally degeneracies of non-Hermitian systems are exceptional points, but it's possible to create diabolic points such as direct points by imposing very special non-Hermitian symmetries, and this allows us to use non-Hermitian systems to explore various sorts of topological properties, including topological phase transitions, Landau levels, and so forth. So as a next step, we are looking into collaborating with various experimentalists to realize these kinds of systems. Thank you very much.
Okay, thank you. If there are questions, please post them in the chat. We have the first question by Andreas Honecker. Andreas, you want to state your question personally?
Okay, since I didn't put it in the public chat, I will ask by sound. So first of all, thank you very much for this interesting presentation. When you were talking about this Dirac cone system in the tight binding realization, so in a condensed matter system, you put imaginary parameters. And I was wondering how should I think about this? I mean, on the honeycomb lattice, you seem to have local dissipation. What kind of physical realization should I have in mind?
Sure. So typically for the people that study these sorts of lattices, non-Hermitian lattices, it is fairly challenging to realize them in condensed matter, for the reason that you pointed out. One way that people can realize them in condensed matter, and in fact you can do it in cold atom systems, is instead of having gain and loss, you basically stagger the loss and more loss. So for example, here, let's say the blue atoms represent gain and the red atoms represent loss. So instead of making this gain and loss, you can make it so that the system has an overall level of loss. And one of the atoms is actually more lossy than the other. You can also realize this in optical systems and other kinds of classical metamaterials, where basically these imaginary parts correspond to the amount of amplification that you apply to the system. For example, in little resonators, you can apply optical gain as you would for a laser, and this corresponds to imaginary part in the on-site mass term, amplification over time.
Okay, excellent. I'm sorry we don't have any more time. So can I please call the next speaker to share their screen and the current speaker to stop sharing the screen. The next speaker is Pinaki Sengupta, also from Singapore. Pinaki.
Trying to share my screen.
Should be at the bottom of your screen. There should be a share screen button in green.
It wants my permission to do whatever it is. Share.
Well, okay. Does it work now?
Will not be able to record contents and I don't need to
Oh, something is happening. Yes, we see your screen. Excellent.
Can you see it in presentation mode?
Now I see the presentation mode. Yes, you're ready to start.
Okay. Thank you. And thank you, Rudolf, Andreas, and Francesca for organizing this. And virtual welcome to all of you. You were supposed to come to Singapore. Hopefully, we can have a physical meeting sometime in the near future. Today I'm going to talk about strange correlations in symmetry protected topological phases. This was done in collaboration with Keola Wiersham, who is currently in Intel Corporation. Here's a brief outline of my talk. I will highlight the symmetry protected topological nature of the Haldan phase, introduce the strange correlator and the results, how we can use the strange correlator to probe the SPT properties. Now, SPT phases form a unique subgroup within the world of topological phases. On one hand, they are the simplest category of topological phases and thus provide an ideal context to study the interplay between symmetry, topology, and strong interactions. On the other hand, they are very poor in terms of characterizing properties. They are not protected by topological symmetry, but rather, they don't have topological protection, but rather they are protected by the symmetries of the ground state. They don't have long-range entanglement, so entanglement entropy vanishes. About they do have the entanglement spectrum exhibits twofold degeneracy, which has been so far the preferred method of detecting SPT phases. What I will argue here is that we can use the strange correlator to probe the existence of gapless edge states. And to do that, let me first introduce the Haldan phase as the canonical SPT phase. The Haldan phase is the ground state of the spin 1 Heisenberg antiferromagnet in 1D. The model itself is not exactly solvable, but if you add a biquadratic term with strength J over 3, then it becomes exactly solvable, and the ground state is known as the AKLT state. Now, the ground state of the Haldan model or the spin 1 Heisenberg chain is adiabatically connected to the AKLT state. The AKLT state, so we can think of the ground state in terms of the AKLT state. The AKLT state is very intuitively very easy to visualize. Imagine each spin 1 moment to be composed of two pseudo spin half moments projected onto the S equals 1 subspace. The pseudo spin halves on nearest neighbor form a singlet on the connecting bonds. So the ground state consists of singlets on bonds, singlets between these pseudo spin halves on neighboring sites. For periodic boundary conditions, the ground state is unique and can be described by a direct product of spin half singlets on each bond. There is a gap to lowest spin excitations, which is known as the Haldan gap. The spin-spin correlations decays exponentially. In other words, there is no local order parameter, no spontaneously broken symmetry. But as was shown, that there exists a string order parameter, which is a non-local order parameter, which can detect or separate this Haldan state from a quantum paramagnet, where you have no order at all. And the easiest way to understand the string order parameter is that it measures the antiferromagnetic ordering between the local SZ equals 1 plus minus 1 states with an arbitrary number of intervening SZ equals 0 states. Remember, these are spin 1 moments, so each spin at a single site, each spin can be in +1, 0, or -1 states. Most importantly for us, the Haldan phase for a open chain has gapless edge states. So open chain means there is an interface between the state and the vacuum. And once again, it's very easy to see intuitively the existence of these gapless edge states. The pseudo-spin halves at the boundary atoms or boundary sites, there is one of the pseudo-spin halves is not connected to any other pseudo-spin half. So they are uncoupled spin halves moments, which can have twofold degeneracy, so that the entire state, ground state, has a fourfold degeneracy. And it is this gapless edge states that we will probe using the strange correlator. So what is the strange correlator? The strange correlator was introduced to probe the existence of gapless modes in symmetry protected topological states. And it is defined as the equal time correlation of a local order parameter or local operator at the imaginary time interface between a topologically trivial state omega, which is this state. We know that it's topologically trivial, and some target state psi, which we want to probe for its topological properties. If psi has topological order, then this strange correlator approaches a finite value in 1 dimensions or decays algebraically with distance in higher dimensions. And this is very useful to probe the existence of topological character for arbitrary states where we do not know the exact ground state, or we do not have, we cannot construct band structures. And can be understood qualitatively as follows. The edge states at the spatial interface, this is the conventional edge state, interface between topologically trivial and non-trivial states have long-range time correlation. If you apply a Lorentz transformation that maps the spatial interface to a temporal interface, then the same transformation maps the imaginary time correlation to real space correlation. And this is of interest to us because this lends itself very naturally to probing using quantum Monte Carlo simulations. In QMC, we study systems, evolution of systems in imaginary time, and temporal boundary, imaginary time boundary is naturally available. What we do is, okay, we have used the stochastic projective version of the stochastic series expansion to study the strange correlator, but different other QMC algorithms can also be used. What we do is we start with a arbitrary state, which we call psi trial, and from both sides evolve one side with the Hamiltonian of interest, whose ground state we want to probe, and on the other side we evolve it with some trivial Hamiltonian whose ground state we know to be topologically trivial. And then at an imaginary time interface where the Hamiltonian switches, we measure the equal time spin-spin correlation. With this, we probe the ground state or topological character of the ground state in this Hamiltonian, which is the spin 1 Heisenberg antiferromagnet with a additional single ion anisotropic term in 1 dimension. This has been extensively studied, and we know the ground state phase diagram very well. For d less than minus 0.31, the ground state has long-range antiferromagnetic order. For d greater than approximately 1, the ground state is a quantum paramagnet where each site is occupied by a spin SZ equals 0 state. And in between, we have the Halden phase. In terms of local order parameters, both the Halden phase and quantum paramagnet are identical. There's no long-range order. The spin-spin correlation decays exponentially, and there is a finite gap to lowest magnetic excitations. And the only way to distinguish them so far has been the string order parameter. Here we show that the strange correlator achieves the same goal. We take the trivial state to be a quantum to be the quantum paramagnet. So we know that for d greater than 1, the ground state is a quantum paramagnet. So for our simulations, we have chosen for getting the trivial state, we have chosen d equals 4. Now, for the other side, the trial Hamiltonian, we have chosen 3 representative values of D to show the validity of the strange correlator. We choose D equals 0, which is deep inside the Haldane phase. We choose D equals, how do I get rid of this? For large D equals 2, the ground state is in the quantum paramagnet. And we see that the strange correlator goes to a constant for the Haldane phase and decays exponentially in the quantum paramagnetic phase. And when we are very close to the phase transition, the strange correlator decays algebraically. And we can fit the data to this functional forms very easy or very conveniently. And proceeding, we can also describe or define a strange order parameter and show that with increasing system size, the strange correlator for the Haldane phase converges to a finite constant value. For the quantum paramagnet, it decays algebraic or exponentially, and in the vicinity of the critical point, the strange order parameter follows an algebraic decay with finite system size. We have also compared the finite size scaling of the strange correlator with conformal field theory of the critical point between the Haldane phase and the quantum paramagnet, and we find that the the finite size scaling obeys similar behavior with a critical exponent which is 2 times the Gaussian model predicted or studied by the conformal field theory. Okay, so far what we have done is show that the strange correlator actually works in identifying the the Haldane phase as distinct from the quantum paramagnet. 4 minutes. Okay. So, but now we can move forward and extend it to where the strange or the string order parameter is not valid. To do that, let us consider the 2-leg ladder, where we have 2 spin-1 chains which are weakly coupled. So within the chains, we still have the Haldane phase, but at the edges, the 2 dangling pseudo spin halves now have an extra interaction which they can take advantage of and form a singlet between the 2 chains. So in this case, there should be no gapless edge state. What happens for the 3-leg ladder? Well, the two of these form a singlet, but now we have the 3rd chain where we have the gapless or dangling spins. So if we look at this strange correlator for the coupled ladders or coupled chains, what we find is that for the 2-leg ladder, the strange correlator decays to 0 very quickly as a function of the system size, whereas for the 3-chain ladder, it decays to a constant. In other words, it can detect the existence of gapless edge states in the finite ladders. What about the extended 2D system? If we have an extended 2D system of weakly coupled chains, then for sufficiently weak interchain coupling, the ground state still consists of Haldane phases along the chains. And at the edges, now we have a spin half Heisenberg antiferromagnetic chain. So that has gapless excitation. And that is indeed what we find from the strange correlator or the strange order plotted here, that the Néel order goes to 0, but the strange order goes to a finite value, indicating that there is no long-range antiferromagnetic order, but there is a finite finite or there exists gapless edge modes. And using this, we can map out the entire phase diagram in the space, complementing the string order parameter. Remember, the string order parameter is valid only when the interchain coupling is 0, but the strange correlator is valid all the way across this phase diagram. Okay, so that with that, I would like to conclude. Thank you for your attention. How did I do in terms of time?
You did very well. We have 1 minute for questions.
Okay.
Who does have a question? There's one by Andreas in the chat window. There doesn't seem to be anyone else with a question at the moment. So Andreas, please go ahead.
Okay, so thank you very much, Pinaki, for the nice talk. At this concerns the beginning, where you used the argument of Lorentz symmetry. Now, the lattice system, usually, if you have a gap, it doesn't really have Lorentz symmetry. That is broken. Does it impact your conclusions, or did you just use that for the sake of argument, or is it still valid close to phase transition? I mean, can you comment on that?
What symmetry did you make for lattice systems?
For the you used Lorentz symmetry to map the time, space and time.
Right. That's true for the continuum, and I used it just to give an intuitive picture for how the strange correlator was first thought of.
Okay, thank you.
Okay, is there any other question? Then I have one, if there really is none. Please be encouraged to ask questions. So the strange correlator is the reason why you use this, not just the string order parameter, because it is a local quantity and hence easier to compute.
That's true, and the string order parameter is only valid when you do not have any interchain coupling. Okay. If you have interchain coupling, so if I go back to the last slide and plot this, sorry.
Yeah, we can see it, it's okay.
Okay, now we know we can map out these boundaries by probing the gap in the system. But I cannot tell anything about the topological character of the ground state at finite values of finite but small values of interchain coupling. There, the string order parameter is not, strictly speaking, not valid. So here the strange correlator goes beyond what is possible otherwise and says that indeed the ground state is adiabatically connected to the Haldane phase even in the presence of weak interchain coupling.
Okay, great. Thank you. There doesn't seem to be any other question anymore that I can see. So thanks.
Sorry, Rudolf, there was one from Daniel.
Okay, Daniel, go ahead then.
Okay, thanks. So in 2 dimensions, don't you have also long-range order with arbitrary asymmetry?
We have long-range antiferromagnetic order for, remember, look at the values of J. These are very weakly coupled chains.
No, but it's still the ground state. It is still the ground state. So
weakly coupled chains. If you have isotropic 2D, then you have antiferromagnetic ordering.
Right, but I would have expected that as soon as you have these other couplings in the other directions, non-zero couplings, then you would have long-range order.
Not quite. Not quite. That's what we found. There is a finite range of interchain coupling where you still have, if I sit at D equals 0, so that this is just a Heisenberg model, then there is a finite range of interchain coupling over which the ground state is gapped.
All right. Okay. Thanks.
Okay, I think we'll have to move on. The next speaker is Laura Hernandez from Cergy. Laura, can you please start sharing, and Pinaki, can you please stop sharing?
Yeah.
And
okay, I'm going just my first time in Zoom sharing screen, so let's cross fingers.
At the bottom of your screen.
I'm there. Let me see. I'm clicking to my open thing. But,
while you do that, I just want to point out to everyone, including the last speakers, that before the poster session, we'll have a big round of applause for everyone. Just out of the interest of time, we're not doing it at the end of every little talk, okay?
Okay, can you see my screen there?
Yes, I can see your screen.
Okay, let me go to the full screen mode. It's okay?
It's black for me at the moment. I can see your screen. Yes, please go ahead.
Okay, so 45. Good. Well, hello everybody. I am going to present a talk that is going to change the sphere of the morning, because I am going to talk about how to study social system with tools of physics, in particular, or the disorder transitions. And this work has been done with Henrik Schave, who is a postdoc in my team, and this work is also part of a larger group with we can hold thanks to a ground of the transatlantic platform digging into data. Okay, so let me just introduce what this is about. In general, models of opinion dynamics, which interest us here, try to understand which are the leading mechanisms that allow for a group of people to agree in the end on a given subject of discussion where the initial opinions were not the same. And there are a lot of models of this. This has been studied since long ago. And most of the models which have a multitude of characteristics like continuous and discrete opinions, full mixed populations or networked systems, they are mainly based in two interactions that are inspired from the social influence on the social influence theory. And these two basic interactions are homophily and social influence. Homophily just means that you like to be with people that are similar to you. It's just birds of a feather flock together. And the social influence characterizes the interaction and its strength, because it seems that when you discuss with somebody, the influence that this person is going to have with you is going to be stronger if this people is already near you in some other aspects of the opinion. Okay. The point is that these kind of models do not consider the situation when changing the opinion may be a cost for the actors. When I mean a cost, I mean that some effort has to be done by the person who's changing its opinion to adopt the new one and to live according to the new opinion. And let me give you some examples that may illustrate that with very popular subjects today. One typical subject of discussion could be global change. If you are a person that is much careless about the problem and you are confronted with the people that are more careful about the subject and trying to change your opinion, you may be influenced by them, but you also have to take into account that changing your opinion and starting to care about the problem implies that you may have to do some efforts, like putting more money to get a less polluting car, or just change your habits by taking less plane and more train and things like that. And at some point, it may happen that you cannot afford that change of opinion. Another example that is very up to date is the reaction of some people to the coronavirus crisis, where they can see that it is better to think that this is just a little problem instead of making the efforts to try to cope up with the pandemics. Okay, So what we are going to do is just to build on this model that I want to discuss a little bit. This is the Haxham and Krause model, which is a very simple model that considers a population of mixed agents, and all of them are homogeneous in their characteristics because they are going to okay, now let me put it another way. Each agent is described by a variable, which is a continuous variable that lives in the 0-1 interval and represents the opinion of the agent. These continuous models are useful when you want to describe a situation in which you are not just choosing among options, but just saying, okay, I am much in agreement with something, a little bit less in agreement, complete in disagreement with something. And so all the agents are carrying an option which is coded in this xi variable, which is a dynamical variable. And this model is called a bounded confidence model because the way in which it represents a social influence is that people are not going to talk with everybody in the society, but only to those whose opinion is not very far from them. And this value, not very far from them, is measured by a parameter which is called here epsilon, and is what we call the confidence. In this homogeneous system, all the confidence are the same and characterize how open-minded or not is the society. And here you have a sketch of the 0-1 interval where all the dots represent the position of different opinions at a given time of the agents, and centered here in the first one, I centered the interval, which is going from its own opinion, x1 plus epsilon to minus epsilon. So this first agent, I don't know if you can see my pointer. It's okay. So this agent will be able to talk to this one at this stage of the dynamics, but not to the others. This model is well understood and has phase transition from polarization to consensus at a critical value of a confidence around 0.2. Okay, but this model is the first one not very realistic because it is not the case that everybody has the same level of confidence to talk to people in the society. So the modification of this model is just to make it heterogeneous and say that, okay, we are exactly in the same situation. And what happens now is that each agent has its own confidence value. So what the agent at each stage, agent I, is going to do is to see around him which are the people that are within its confidence value and update its own opinion as the rule that is put here. So as you see, here you have again the 0-1 interval, and the agents have colors because they have this idiosyncratic property, which is its own confidence. And you see that those are the bars with the same color that are just below. And this model already integrates a very important ingredient, that is that if you do that, the interactions are not symmetric anymore. And what you see is that, for instance, the fact that the blue agent will take into account the red agent's opinion doesn't mean that the other is going to do the same. Okay, so very recently, there has been an extensive work that we had also done with Hendrik, and what we have measured is how this heterogeneity modifies the initial model. And what you are looking here is a phase diagram, which is displayed between the different intervals of confidences where you can set the values for your population. How you read that. So one population is going to have confidence within an interval determined by epsilon lower and epsilon upper. So each point of this diagram is one society. You're going to draw the confidence of the agents within there, and you're going to run the dynamics that we have described before. And you're going to measure the order parameter, which is the size of the largest cluster of individuals holding the same opinion. Okay, so the interesting point here is that you find the very non-trivial structures in the phase diagram, and in particular, the one we are interested here is this re-entrant consensus phase that is completely non-trivial. Because what happens here? Imagine that you are situated in this region of lower bound. That means that you may have in your society very close-minded people. As you increase in this line, vertical line, you incorporate more and more open-minded people. So you pass from the dark region in which you don't have consensus, and then you find the yellow region when you have full consensus, and this is completely normal. The astonishing part is that when you continue incorporating open-minded agents, this consensus is destroyed. So I'm not because I'm just gonna build on this model, and I just encourage you to see Hendrik's poster later because he's gonna tell you everything about this. Okay, so what we want to do is just to add to this previous model the notion of a cost. That for us is very agnostic, doesn't necessarily mean cost in terms of money. So what we're gonna do is to couple the dynamics of the resources of the agents with the Hexelman-Krauss dynamics for the heterogeneous model. And we're gonna endow the agents with initial resources distributed in some interval, and we have tested different distributions that we're gonna discuss. And we're gonna say that each time that the agent is gonna change his opinion, he has to pay some effort, and the effort is going to be proportional to the change in the opinion the agent has done. And this, eta is the proportionality parameter. I mean, how much it's cost each opinion change, and it's going to be our disorder parameter in the model. What happens when the agent loses all the resources? Well, it cannot afford more opinion changes, but it doesn't leave the society. What is important, it doesn't evolve anymore, but it can stay there and maybe unattractive for the others. Okay, so let's very quick around the dynamics. The dynamics is exactly the same as before. So you look for your neighbors with heterogeneous confidences. If they are inside, you're going to try to make this change. But you can only make this change if what you have to pay is something that is still in your budget. You still have resources to pay that. If you don't have those resources, then you just go as far as you can, or you stay where you are. That's all. And also the resources diminish in time, proportional, as I say, to the difference of opinion that you have got in that moment. Okay, so first let's have a quick look at what happens with the phase diagrams. The first important thing is that your phase diagrams lose the structure as you see the eta parameter increases going to the right. What we can study now are the different zones that we can extract from the initial parameter without cost. Here you have represented by A is the region of the reentrant phase, B is the yellow region of full consensus, and the green and bluish are those that are complete fragmentation or polarization. And we're going to concentrate on them. We're going to see, as I told you, that this reentrant phase disappears with the cost. So let's see what happens in the most interesting region, which is region A. Let's see first the dynamics in this region. The first case, what you have here is the, in the vertical axis, you have a set of opinions selected over a very large system. Randomly, there are only shown 100 opinions for visibility, and then you have evolution in time. What you are having here is that you are in this region, so you have a very low upper bound, so you have very close-minded agents and some intermediate-minded agents. And what happens is that the dynamic goes, but open-minded agents can drag the close-minded to the average value in the middle because of the symmetry of the model. But if you start putting cost, what happens is that those light blue agents appears, which are freeze, and they may freeze because they don't have any much resources to afford changing the opinion. And so they drag this initial bell for a little longer and delay the consensus to form. But the consensus can still form, and you see some agents that are fixed but near the consensus opinion. But if the cost is higher this may happen from the start. And then you're going to split these two branches that will never be able to join again, and you get a transition to polarization. So this is what is happening. Interestingly, what we have found is that this is a real phase transition, in the sense that you can detect that it goes to a sharp transition in the infinite limit. And here you have the scaling of the order parameter. In the inset, you have the order parameter brute, and here you have the order parameter that has been scaled by this formula in order to see the collapse of the curves. And you have here the exponents A that are robust for all different types of distribution of resources, and whether they are correlated or not with the confidences in this region of the reentrant phase. I'm gonna go quickly. This still holds for other values of the region. So here you have a smaller one value is still the same, and it also holds for a homogeneous case, which is a dot that is situated here in the diagonal. We have tried different distribution of resources, because initially the distribution of resources was homogeneous, and this may look like not very realistic, but we have seen that again you can collapse and see the same transition with the same exponents when you get a half Gaussian, and even when you introduce correlations in your system between the resources and the open-mindedness of the agents. In this case, an anti-correlation. The simple correlation does nothing. But again, you don't find any qualitative difference. You always have this phase transition in the thermodynamic limit, with one interesting exception. And this exception is when you don't have in your population, you don't have very poor agents. Look here, the initial resources have been cut. The very low resources are not there anymore. We're starting 0.3. The fact that we go to 0.7 is to always get the same average resources per agent initially to compare between them. But we also check that if you put up to 1 is always the same. And this is very interesting because these are brute results. So this does not depend on the size, and you will not get a sharp transition in the thermodynamic limit. So when you don't have very poor agents in the society, you don't have this sharp transition. Now, in the other regions, the things are much smooth. You have, again, a smooth decrease if you start with a bounded interval confidence in this region, which you remember was the yellow one. We were always having consensus, so everybody's open-minded. The fact to increase the cost of your opinion change just goes to a tranquil, I mean, slow decrease of your order parameter, but you don't have a transition. And you have the collapse of all of them in the brute data. So this is not going to change with the size of the population.
1 minute,
and the
Laura.
same happens in this region, which is already less interested because already you don't have consensus at the beginning. So just to wrap up, we have studied the heterogeneous diagram, and we see that as the phase diagram of the heterogeneous model, and we have seen that the reentrant phase and the complex structure is washed out by introducing the consensus. You also found that in a society with open-minded agents, the increase of the cost of opinion change just leads to a gradual decrease of consensus. But if you have a society where you have mixing agents with intermediate values of confidence, and also which have very low values of confidence, if you increase the cost of the opinion change, then you get a sharp phase transition in your society. And this can be avoided if in your society you prevent from having very poor agents. So this is all. I am thanking my collaborator again, and just the financial help, and thank you for your attention.
Excellent, thank you very much. We have 2 questions. Pinaki Sengupta first, please.
Laura, you showed in the original HK model and then again for eta equals 1.1 that there is a stabilization to 2-fold opinion.
Yes, the transition goes to polarization.
So are there multiple points also, like 3, 4?
You mean different number of opinions? No,
right.
The transition goes first to polarization, but then if you increase a lot of the cost, obviously you finish with everybody frozen and you have a lot of opinions if you go to extreme values of the cost.
I see. So it's either 1, 2, or infinite.
Yes, but then you have to increase too much. So the first transition is just to polarize your system. I mean, you have a society agreeing on something and all of a sudden they just break and you got opponent fields.
Okay, Christian, please. You're still muted, Christian.
Okay, yeah. Nice talk, I mean, Laura. I'm just, changing a little bit my question, okay? My question first was, can you adapt this type of models, to, for example, for branding, political influencing or whatever? But in doing so, you need to have a kind of a basin of attraction or something like that. You have an opinion somewhere, you have another opinion somewhere, you could have, conflicts between these basins of attraction. And these models can target this type of situations or not?
Yes, they can, but in general, you use for that, you don't use in general continuum models because then you have options. Okay, so you have a set of options, and in general, you use discrete models to do that. Mm-hmm. And there has been a lot of studies with discrete models that introduce, for instance, an external field as the influence of mass media and so on and so forth. So this particular model is more adapted to situation in which you say, I much agree, I little agree, I less agree with something.
Okay. Do you allow me to ask a quick one or not?
Yes.
Yes. Okay. Thank you. Okay, of course, you could imagine studying this type of things with kind of an easy model or something like that, okay? And having on each node of your lattice, many options with kinds of a pot model or whatever you want to call it. Okay, my question would be, do you think, or do you know, if quantum models to try to get the sociology of this type of situation could help or not?
Well, okay, the other models you started talking about, obviously all the physicists started by that. So there is a huge literature on the icing and pots and whatever you want about that. About the quantum version of this, I don't know what you're thinking about, the kind of entanglement, or I don't know what is the idea. There is no, up to my knowledge, there is nothing related to that. But I don't know what you have exactly in mind to introduce kind of quantum thing. I guess entanglement in some way.
Entanglement, yes, indeed. Some entanglement entropy, yes.
Right, I'm cutting in here because I think this is not going to stop this discussion. Let's move to the next talk. Let's move to the next talk. Thank you very much. Laura, the next talk is by Bobby Tan.
Okay, I have to stop this. I don't know.
Yes, just stop sharing the screen at the bottom again. Stop sharing your screen at the first. And Bobby, you should be able to start sharing the screen already.
How do I do that? I don't see anything in my button. I have to get out from the screen. Okay.
You probably, yes.
Stop. No, it's in top. You were okay. It's okay now? Yeah, it is.
I don't see your slide anymore. I think I see
there is a new one coming.
Yes, so we're ready.
Yeah. Mm-hmm.
Bobby, are you ready?
Yes, I'm ready.
All right. We don't see your video. Could you put it on your video?
Give me a moment to find the option.
It's just a little bit more human.
Oh,
it's
okay.
not a robot speaking. Okay, please go ahead.
So, see my face? Everything good? Voice clear? Okay, so allow me to start. So I'm Bobby. I'm currently a postdoc in NTU. So the topic of today is negative probability distributions, and hopefully by the end of today's talk, you'll realize that negative probabilities are not so exotic after all. So this is the basic outline of my talk. First of all, I'm going to discuss the notion of non-classicality in light and how in relation to this negative probabilities really emerges. And I'm also going to discuss several properties and interpretations of such negative probabilities. And this is basically a list of references. The contents of this talk are basically taken from these papers. And in particular, if you are interested to know more about non-classical light sources, the first is a review paper that covers these topics. And this is work done with several collaborators, Hyuk Jung Kwon from Imperial College, Tyler Volkov from Los Alamos National Laboratory, Sung Jun Choi and Hyun Suk Jung from Seoul National University. So basically, what is non-classical light? In the classical harmonic oscillator, so basically you can fully describe the state of system as a single point in phase space. So if you have exact knowledge of the position and the momentum of the particle, then you can predict, right, the evolution of the entire system. But in quantum mechanics, this is not really possible because of the uncertainty principle, right? And because the oscillation of an electric field can be essentially mapped to a quantum harmonic oscillator, an electric field, an oscillating electric field, also suffers from the uncertainty principle. And this is basically equivalent to saying that we cannot know the amplitude and the phase of a light wave in this picture. So what this basically means is that quantum mechanics does not allow for a perfect description of a classical system, right? But we can still ask the question, what state in quantum mechanics is the closest to a classical system, classical harmonic oscillator? And in this sense, the answer to this question is a minimum uncertainty state, right? So basically, instead of having a single point, instead of having describing the system by using a single point, we replace a point with a circular kind of distribution, and only one kind of state of light qualifies as this classical state, and this is the set of so-called coherent states. And usually the way they're defined is as the eigenvectors of the annihilation operator. And in general, the coherent states have complex eigenvalues, and the complex number alpha essentially gives you information about the center of the distribution in phase space in this picture, right? So you can visualize the coherent state alpha as some sort of a Gaussian distribution about some center x naught and p naught, and an example of a source of coherent states is in fact just standard laser, right? So let's say you take the output of a laser and you try to sample its electric field. You find that inevitably, if you sample the electric field, there's always some uncertainty about its phase as well as its amplitude, and this is inherently because of the uncertainty principle. So if you accept this argument that somehow coherent states are the most classical pure quantum states, then if you consider on the level of density matrices, then any convex mixtures of coherent states must also be classical. So in this case, by convex mixture, I just mean that the density matrix of a state can be written as a form of a distribution, probability distribution over the coherent states, right? And in this case, this probability distribution is just a standard positive probability distribution function, so it's always positive. But the story doesn't end there, because it turns out that you can arrive at a similar expression not just for classical states, but for any arbitrary states of light. So it turns out that you can in fact express an arbitrary state of light in a similar way in terms of the coherent states. But the caveat is that this coefficient here, instead of being a probability distribution function, you have to allow for negative values, right? So this coefficient P alpha has a name. It's called Glauber-Sudarshan P function. And it's a quasi-probability distribution function in the sense that it always sums up to 1, but sometimes it can have negative values, right? So we see that in quantum optics, negative probabilities emerges when we study the classical, non-classical correspondence. So if the P function is always positive, then we say that the quantum state is a classical state. And if it displays some sort of negativity, then we say that the quantum state is a non-classical state. So such non-classical states have many useful applications. One of them is that if you have, let's say, a source of non-classical state, you can pass it through a beam splitter and the output will be entangled. So this is one method of generating entangled states for quantum communication. And non-classical states of light is also known to be useful in quantum metrology. For instance, it can be used to improve the sensitivity of the Mach-Zehnder interferometer, and where you can show that non-classical states of light, such as squeeze states, for the same brightness, they can be more sensitive than classical sources. And such properties are being exploited, for instance, in LIGO to detect gravitational waves. So that's nice, right? Like essentially we can determine whether a state is classical or non-classical just by studying the Glauber-Sudarshan P function. The main issue with the P function is that it has a NaN problem, and NaN in this case means it's not a number. So for instance, if we have the Fock states and you try to calculate the P function, you get an expression, but it's higher order derivatives of the delta function. And really, because it's not a number, it's not really easy for us to interpret what this function really means, or to visualize what is happening. So because of technical difficulties, right, physicists generally prefer to work with quasi-probability representations other than the P function. So how do you get other kinds of quasi-probability distribution functions? One way to do this is to apply a filter. So what this means is that, let's say you have the P function, you can apply an inverse Fourier transform, and what you get is the characteristic function. And unlike the P function, the characteristic function is always just a regular function. It outputs a number, right? So to this characteristic function, you can apply another function called the filter function, omega, and then you perform a Fourier transform again. And for certain choices of filters, right, the resulting distribution function is still a quasi-probability distribution, right? So for instance, we can choose the filter to be a Gaussian one, right? So in this case, I have parameterized the Gaussian filter with some parameter S. And in fact, if you apply this filter and try to get the resulting quasi-probability distribution function, it has a name. It's called the S-parameterized quasi-probability, right? And if you put in different values of S, it gives you different kinds of quasi-probabilities. So if you have S equals to 1, you just retrieve the original P function. But if you put in S equals to 0, you get the Wigner function, right? And you put S equals to 1 equals to -1, you get something called the Q function. So generally speaking, it is known that if you set S less than equals to 0, there is no NaN problem. So you always get a regular function as the output. But the price to pay is that certain kinds of non-classical states cannot be detected. So for instance, it is known that the Wigner function is not really good at detecting squeezing. So it cannot detect non-classicality that comes from, for instance, the squeeze states. So, so one possible solution to this is that instead of considering a non-Gaussian, instead of applying a Gaussian filter, what we try to do is to apply a non-Gaussian filter. And in this case, what my collaborators and I did was that we chose a very specific kind of filter with some mathematical properties, but the most important one is probably just this one. So we choose some filter such that if you let W go to infinity, right, this function eventually tends to just 1. So basically it does nothing.
Bobby, a minute and a half warning.
Sorry?
You have a minute and a half left.
Okay, okay. So that means I really have to speed up. So the basic idea is that instead of dealing with the P function directly, we apply the filter and then get a function that is always a regular function and just let W tend to infinity. So this allows us to avoid the NAND problem. And what this means is that this allows us to consistently define the negativity of the distribution function. So in this case, because it always outputs a number, we can just sum up the negative probabilities, right? And one property we can show is that if you have some kind of map which represents linear optical operations, if you apply a linear optical operation to a state, it can never increase the negativity, right? And this is very important because in quantum information, non-classicality measure doesn't make sense if a classical operation produces non-classical effects. So we have to have this condition. So this allows us to justify the use of negativity measures in other parts of the literature. And we can also show other properties, for instance, the monotonicity of the negativity when it's parameterized by S. And we can also show that the negativity has some sort of operational interpretation in terms of the robustness. So robustness basically asks a question. So if you mix a non-classical state with a classical one, how much mixing do you need before all non-classical effects are erased? So it turns out that the negativity directly quantifies this. And we were able to show this property because we applied these kinds of filters. And that's basically the gist of my talk. So any questions?
Thank you very much. Yes. Does anyone have questions?
Okay. Nobody else wants to ask a question. So sorry if I slept, if I didn't pay attention. But I was wondering. I might have missed something. I was wondering how, okay, you say that these negative quasi-probabilities correspond to non-classicality, but do you have direct access to that physically? I mean, can you observe them physically in a direct manner?
Okay, so for instance, one way to observe these, negativity is one way is just to perform tomography, and then you can get the distribution functions. But I assume that you don't want to perform the negativity and to decide and to obtain the full distribution function. So one thing you can do, for instance, is to make use of this property that if the input state here is non-classical, you pass it through a beam splitter, resulting state is entangled. So if we know that the output is entangled, there are a variety of, for instance, entanglement witnesses that you can use to detect the entanglement in the output. And this is an if and only if condition. So you can always tell whether the input state is non-classical or not. So I hope that addresses your question.
Sorry, but I get the impression that the negative quasi-probability has no direct physical meaning and therefore no conceptual problem. I mean, negative probabilities are not so nice, and
I mean, negative probabilities does have direct physical consequences. So for instance, in this case, it produces an entanglement through the beam splitter. In the second case, it increases the sensitivity of interferometers. So there's real physical consequences. I think what you're referring to is the fact that negative probabilities don't have an interpretation as a probability, right? So, but that's not really an issue because we have real actual applications for states with that displays negativity as a property, right?
I think negative time is also very horrible, and we're already 7 minutes in negative time at least. Okay. So I'd like to thank Bobby and switch to the next talk by Dario Poletti. Dario, can you please start sharing your screen?
Hi.
Okay, looks like you started screen sharing.
Can you see my screen?
It's on screen, yes.
Very good.
Go ahead.
Okay, so you are seeing my slides. It's nice. It's open. I can't see very well.
But it's not the presentation mode yet. We just see the individual slides.
Okay, now?
Now it is.
Okay, very good. Thanks. So thank you for giving me the opportunity to talk about this work of mine, and welcome to my place. We're working from home still. So today I want to tell you about tensor network-based machine learning of non-Markovian quantum processes. It's quite different from the topics we heard until now. So I will try to tell you first of all about the open quantum system and this object which is called the process tensor. Maybe not so familiar with everyone. And also I will, at the beginning, I will give a little I will say a few words about MPS and MPOs, matrix product operators, which is a tool that I will need to analyze these systems. And then I will tell you about learning with MPOs, generic open quantum system processes with the process tensors, and then I will go through the conclusions. So let me start by saying just a few words on MPS and MPOs. If you have a mini body system, let's say, for example, a spin chain with different spins at different sites, and then you can describe this with a vector, which is a size which is, grows exponentially with the system size. Okay. Now, one way to describe this more efficiently, and for a certain class of problems, say works perfectly, for another class of problems can be a very good approximation, is to use a matrix product states ansatz, for which the coefficients are written as a product of matrices. Now, if to have exact representation of all the coefficients, these matrices should have a size which grows exponentially also with the system size, but it turns out that you can truncate it to a finite size which we call the bond dimension, here capital D, and then you can still describe even perfectly some a large class of systems, and fairly accurate and larger another class of systems, and not well at all other systems. Okay, but there are cases in which it works really well, and it is very efficient. There is a graphical representation of matrix product states, which is this one here. So let's say our coefficient can be seen as each coefficient as one element of this tensor, which is composed of a smaller tensor, which have one physical index and two auxiliary indices. Okay, and the size of these auxiliary indices is what we call the bond dimension. Now, what an MPO is, which is a critical thing I need to discuss now, it's a linear operator that acts on matrix product states, and graphically is represented in this way. So it goes from some physical states to other physical states, and is composed of 4 legs tensors with two auxiliary indices, but this time 2 physical indices. Okay, so this is the very brief introduction on matrix product states and matrix product operator. So now let's go to the physics and why I'm talking about this and what a process tensor is. So I want to consider a system which is coupled to an environment. I want to describe the evolution of the system. Now, what is important is that we need to take into account, and this system can be anything, can be, I don't know, quantum device, quantum computer, whatever. So three things we need to take into account. One is the coupling of the system with the environment, okay? But then also we can do different operations or preparations on the systems. After a while, for example, we can choose to change our system while it's still coupled to the environment. So the environment has a memory of what the system was like before, okay? And also we can do measurements on the system, which at the same time can affect the environment and so on. So we need to keep into account these three things. The interactions between system and environment, the preparations that we can do on the systems, and the measurements. And there is one object that takes into account all of this, and it was discussed in these two papers in 2016 and 2018, and it's called the process tensors, which in this presentation we refer to as upsilon, this Greek letter here. Okay, so to give a bit more insight on what this process tensor is, let's suppose we take a system, which is our ball here with the 0 number. And then we consider an environment with various other spins. And then we let them evolve, and the evolution of this is given by some operations, which here I write as MPOs acting on system environment. And then I can do some preparations, some measurements, which here are indicated by these lambdas, at different time steps after certain DTs. Okay, I can do something, I can choose not to do anything, but I could do some measurements and I can do some other preparations. Okay, so this is a generic actions that I can do. And if I look at whatever is not the system and what I choose to do, and basically it's what is highlighted by the blue background, and I take it out and I look at it, this is what we call the process tensor, okay? And you can see that it has some different legs that connect this object to our system and all the possible measurements and preparations that we do. And by little, just little pictorial transformation, you can see that you can write this as an MPO, because you have this physical indices here, this physical indices here, this physical indices here, and which would be the ones here. And then these MPOs will be connected by some auxiliary indices here, okay, which would then be of a certain size, which we'll describe later, okay. So a generic process which includes coupling of the environment, preparations and measurements can be described by an MPO, which is called the process tensor. Now we want to see whether generically we can learn this process tensor, which will tell us everything about the environment. And then in the future, maybe let's say we do a certain number of experiments, we get our best approximation of what this process tensor is, and then we know what will happen if we do different types of preparations or different types of measurements. Okay, so this is the idea. And the way we do this is building on a previous work done in SUTD, my university, with one of my former PhD students and some colleagues in computer science, experts in natural language processing. And what we did here was to find a way to use an MPO basically as they call it an exponential machine, or basically a linear neural network in a sense. So the way it works is this one, the way we built it was to do a sequence-to-sequence learning. I have to say that the use of tensor networks or matrix product states was already started by two very nice work, one by Stoudemire and Schwab in 2016, and other works by the Panzang group in 2018. But they were doing only classifications. So we extended this to sequence learning. And what it means that given a vector, we want to be able to predict another vector. And the way we train the MPO is by taking a vector, converting to an MPS, which is a trivial one-dimensional one MPS. And then from these two input and output MPSs, we train an MPO. And then we can use this MPO when multiplied by another MPS to predict, to have a prediction MPS output, which can be converted to a sequence. And so like this, we can use MPOs to do sequence-to-sequence learning. And we applied this to cellular automata evolution, nonlinear diffusion equations, so on and so forth. Here, now it becomes very natural to think, okay, my MPO can be the process tensor, and I can look at different types of preparations, which would be the blue inputs, and measurements, which would be the red. And then by using many samples of preparations and measurements, I can figure out what is the MPO, and then I can characterize the open system dynamics. Okay, so the way we do this is fairly simple. Once we have the exact output, we have a predicted output, which is given by the application of our vector over the MPO. And then we have a regularization term in our cost function. And at the end of the day, this becomes like doing DMRG and finding the ground state. Instead of finding the ground state, we find the minimum of this cost function by optimizing over our MPOs. And this is a graphical representation of the calculation that we do. I'm happy to discuss more in detail or even offline about how to do this. So once we have this tool available, we can use it for our system. So how do we prepare our input and output states? The way we do this is using basically this circuit model. We have our environment here, E, and then we have our system at initial preparation, then next preparation, and so on and so forth. Then the input goes in, couples to the environment, something comes out, and then we do swap gate, it comes out, and then we have our output here, okay, from over which we can do some measurements. And then we have the other input that has come in with swap gate comes in, evolves, coupled to the environment, and so on and so forth. So you can see that if the environment has a long memory, whatever was an x0 will still matter for when you input the x and minus 1, because there will be a memory of what happened before here. Okay, so now what exactly we do, we take a system which will just one spin, and we just take 3 spins as environment, and we couple the environment also to some Limrad buff to facilitate thermalization or some relaxation, at least. Maybe not thermalization is not the correct word, some relaxation. But let's be careful. Since we are looking at different time steps, for each time step, we need a different spin. So if, for example, we measure 6 different time steps, we need a system of 9 spins, 6 for the different inputs, and then 3 for the environment, okay? Also, you can ask yourself, what would be the maximum size of the bond dimension of the MPO that I need? And this is actually given by the size of the environment. So how much memory you can have in the environment cannot be larger than how much you can store in the bits that you have in the environment. So since each environment spin is basically can be described by 2 by 2 matrix, roughly is 4 to the 3 is actually less. The memory, because of course these are physical. Okay, so this is what we have. We also have a bound on for our system to how large the bond dimension can be. So now we can let me give you a little bit more details of the Hamiltonians and the dynamics of the system and the environment. For the system, we have just a magnetic field in one direction. For the environment, we have we put like an XZ chain. And now our system is coupled to every single spin of the environment, okay? And the coupling between the system and environment is characterized by this J, okay, which we will tune. While JE here will be like a scale for the system, will be fixed to 1 and H bar fixed to 1.
Dario, 3-minute
yes.
warning. 3-minute warning.
No problem, thank you. So here, the spin is also coupled to a buff, which can reset the spin of the environment, maybe to the pointing down, all the way pointing down, or all the way pointing up, or somewhere in the middle, depending on these parameters are. Okay, if it's 0.5, we're setting up the buff to the infinite temperature. If it's somewhere, if it's 0, 1, where all the spins tend to be pointing down or pointing up. Okay, so let's look at our results. What are we looking at? We are looking, for example, at locally the density matrix, what it looks like. This is one of the things to look at. Or we look overall, all of the outputs, or we look overall what the process tensor is and whether we can represent it correctly. Okay, Okay, these are maybe small details. I will not talk about it. We look at the infidelity, and we try to reduce the infidelity of our prediction compared to what the exact results are. And let's look at just the three different scenarios. Scenario number one, we put in the buff, we put absolutely unitary evolution, like gamma equals to 0. And this is represented in this curve here. Even if we increase the bond dimension here, you don't see very well, the bond dimension to represent our buffs, since the bond dimension even with 6 or 8 auxiliary states is not able to represent very well all of the dynamics, the infidelity doesn't come down so much. But if we put some dissipation in the buff, then there will be memory losses, and then even a bond dimension equals to 4 is able to describe very, very accurate the system because the infidelity goes down significantly. And similar ideas come if we put a weak or strong coupling to the buffs. For example, for weak coupling to the buff, it's very easy to describe the dynamics. We get to an infidelity of 10 to the minus 5, which is the numerical error of the evolution for us. So very accurate descriptions. While for j equals to 4, strong coupling to the environment, then we need more larger bond dimension to describe our system. So the system is much more non-Markovian. And something interesting is, of course, we can try to train our system, put a lot of training samples, but if you don't have enough large bond dimensions, it will be pointless because we have the best description we can have for a given bond dimension. So we can see here that if I choose a small bond dimension, I can choose as many training data will not improve at all. But if I choose a large bond dimension like d equals to 10, as I increase the training data, I can get a better description of the system. And I can also try to describe the full process tensor. Maybe here I just describe this figure here, the full process tensor epsilon. I try to describe how accurate my description of epsilon is. And what I can see is that if I increase the number of training data, my description improves as long as I have a large enough bond dimension. So if I have a bond dimension about 20, then I can go down and get a very good description. Until a certain point, if my bond dimension is too large, then I get into some kind of overfitting. And then eventually my prediction can get worse. And that's why here it comes out again. So I conclude, more or less, I think in time. We show how we, for a generic process, open process, where there can be coupling to the environment, different types of measurements and preparations. This dynamics can be described by a process tensor. And this process tensor is basically an MPO. And we know how to learn MPOs by looking at by producing different preparations and different measurements. And like this, we can try to learn the dynamics. And by looking at, for example, the bond dimension, we can figure out whether the dynamics is Markovian or non-Markovian. It would be Markovian if bond dimension 1 is enough to describe the whole system. And of course, now we are hoping to apply this into some real experiments, maybe with NV centers or maybe with some of the available quantum computers. Thank you very much.
Excellent. Thank you very much, Dario. Can I have some questions, please? I have one from Andreas Honecker. Andreas,
Okay,
go ahead.
Dario, thank you very much for the nice talk. The question I have concerns terminology, and so you might understand using TensorNet, applying machine learning to tensor networks in two ways. You can use the tensor network to replace actually a neural network, and so then basically try to train a matrix product state rather than neural network in order to classify something, or you can say that you want actually to learn in a neural network the properties of a matrix product state. And if I understood correctly, you meant the former, yeah? So just a clarification.
Yes, so we know that what we want to learn can be exactly described by an MPO. And so what we want to learn is exactly the MPO, and we know how to learn MPOs. So our neural network for us is really is a tensor network. And we use DMRG-like techniques to learn our MPOs. So that's what we do. Does this answer your question?
Yeah, then if I may, it looks very close to the original algorithms that you do. How far would this generalize? I mean, could you apply this to other situations?
Yes, actually in our previous work when we, so first of all, the first work by Studenmeyer and Schwab in 2016, they used this for classification problems. And for example, they use it for the typical NIST digit problem. Later on in 2018, MPS neural networks were used to do generative models. And what we did was to do sequence-to-sequence learning. And for example, we trained the dynamics of some non-trivial cellular automata. And also, but these are all linear problems. So we wanted to do also something non-linear, so that this can be used to learn non-linear dynamics. So we also studied anomalous, non-linear diffusion processes with also some long-range couplings and so on. And it was able to perform better than bidirectional neural networks with LSTM cells. Okay, and so it is actually fairly powerful. We tried to use it also for natural language processing, but the one that was not working very well. We need to work harder. But
we have another question, if I may interrupt, by Javad Fahedi, I think. Javad, you have your hand raised.
Hello, can you hear me? Hello?
Yes.
Okay, thank you for the presentation. So one question regarding the time, because as I know, TDMRG based on MPOS usually has a problem in some specific model. They violate the area law. So related to the time, how long can you go and detect your process and this kind of stuff in your approach? If you back to the sum of your figure,
yes.
For example, if you back 2 or 3 slides before, so here you put a time, as I understood. Could you go ahead one slide?
No. Yeah, let me slowly go.
So my question is the limitation of the time in your approach.
Okay. So I think the better figure is this one to look at. You can see the x-axis will be time. Now, all these operators here are MPOs that we know, okay? And what we need to see is whether we can describe the MPO up to a certain scale. Now, how much it will increase the size if you have absolutely no memory losses. And we go like the size of these to the power of number of time steps, basically, okay? But fortunately, we are considering systems which have some memory loss. So eventually, you will be able to, if you cut vertically like this, if you have enough memory loss, you will be able to go far enough in time. Now, if the system is highly non-Markovian and you don't have enough memory losses, then it will be very complicated. If it's only unitary evolution and your buffer is very large and maybe your buffer is actually integrable and it doesn't relax or whatever it is, then it will be very, very hard. So it's kind of system dependent. But if, for example, in the limit, the dynamics is Markovian, then we can describe this environment very easily, as long as our system is not too big. Okay, so there are two difficulties.
Okay, so the result you show here was for very small systems, just a few number of atoms spin in the environment. Do you have roughly estimate how big the system you can go with this type of approach, or did you do any test with your approach, how you can go for?
Okay, so two things. Number one, you see, look at this dissipator. If this gamma is large enough, for example, and this brings it to the infinite temperature state or close to the infinite temperature state, so R is close to 0.5, we can go to very, very far in time. That is not a problem. Because the environment will always be described by something which has a small bond dimension. Another thing I have to say though is that something that if we want to compute exactly the MPO when we train it, we also have to simulate the system. And even if the system is small, like here, or just one spin, but if you want to do 10 time steps, then we need 10 copies of the system and 10 different, sorry, non copies, 10 different preparations of the system. Okay, so that could make some calculations harder. But if you are only looking at the environment, things could be for systems, a certain system, fairly easy, depending on this dissipative part or depending on the dynamics of the environment. Or it could be extremely complicated. Yeah.
Yeah, thank you.
Okay.
Thank you.
Could you please all turn your microphones? And first of all, let's thank all the speakers of this morning by giving them a bit of an applause.
In future, further sides. If this is energy range is a band gap range between 1.7 to 1.9, and if you are going to the bulk material, it's a 1.2 electron. It's a good agreement with the previous calculations. And we are going to make we would like to make the twisted bilayer. How we are going to make the twisted bilayer of MOS2? We just take the simple AA stacking and we just rotate the one layer is keep it rest and another layer is moving some angles like a twisted bilayer graphene. Here we are taking the NM formula. Here N and M are indicates the integers. Here is a capital N is indicate total number of atoms in the structure. So present case we are showing the one of the example based on this formula. We can make the 13 degrees. 13 is the top and the side view of the 13 degrees angles. Here is the distance between the MO and S and SS. After that, we are going to use this Abinit software program. We are calculating the electronic band structure for the large angles. With the large angles, see 21 degrees, 13, 9, and 7 degrees. If we are observing this one, here is we can observe the conduction band in the parabolic curve at highest symmetry point. It's not affected by the theta while you are changing the theta. And also here we can observe while we are in the monolayer case, we can observe the S state is not also. It's not affected by theta. That's why we are fixing the state as 0, and S1 is not also, it does not vary slightly with theta. The variation is occur only in the states S2 and S3. If you are observing the different angles and the different colors, we are observing this one. So we are going to study mainly in the valency band study. So we would like to further go into the small angles using DFT calculations. It's very expensive by the CPU time and the memory. So that's why we are going to construct the tight banding model. So here is my tight banding model. This is the 11 band model twisted MS bilayer, MS monolayer. Here is the Hamiltonian, this one is indicate the on-site energy, this one is indicate the hopping parameters. Here we are taking the nearest neighbors of MO and the MOS and molybdenum sulfur. These are colors indicate the corresponding the nearest neighbors of molybdenum and sulfur and molybdenum and sulfur. Here is the on-site energy of the d orbitals of molybdenum and s orbitals of sulfur of p orbitals. This is the answer to that question. Based on these tight banding parameters, we are construct we are fitting the parameters in the first principle calculation. Is a good agreement around the band gap region. Here is this one band gap region. We have fixed the state S0 and S1 for the future purpose. This one is a Brillouin zone. This is a symmetry. This is the highest symmetry points and gamma, K, and M. And we are moving this is a monolayer case. We want to construct the twisted bilayer MOS2. So we are taking the interlayer construction. Here we are going to these are mainly exponential decay happening with the two parameters Q and D minimum. It is my simple bilayer case. Which one is? Many researchers have done this one, taking the simple sulfur stacking, but we found it's a molybdenum sulfur and molybdenum also very important for the around the band gap region. That's why we are including this interaction MO and MOS. So we are fitting these parameters like here for the 21 degrees and 9 degrees. Around the here excellent agreement with the highest valency bonds in the here 21 degrees and 13 degrees. and qualitatively is good behavior, good in the conduction band with both angles. So we are taking the reference of this one, the Slater-Costa tight banding model. We are making the band analysis, like we make the all the like smallest angles. So here I present the 7 degrees of the band dispersion, like this one, highest valency bands here, and energy versus moment and space. So if we are observing these one, state S2 and S3 are linearly varies with theta square here, linearly varies with theta square. This strongly indicates that there is directly consequence of Morris structure. This Morris structure. After that, we are going to find the energy gap between the S4 state and S2 states. We get some mini band gaps after the here we get some mini band gaps. We are going to the less than 6 degrees. So we got some mini gaps in the other valency band. Okay. Then this is also, this is a response. This one is not isolated one, non-degenerate, but it responds to the one state for Morris shell. And after that, we are going to calculate the slope between the highest valency bands between the state S2 and S3. That means K1 between K and M. This result, like a slope, is directly proportional to the intra-band velocity. After here, we can observe that after 2 degrees, we are going to the velocity is going to vanish. These results show that the electronic confinement is directly corresponds to the flat band. That means it look like it's similar to the twisted bilayer graphene. Similar to that one. Then we are going to construct the Mori pattern. Here we are present the nice Mori pattern. This black line indicate the unit cell. On the corner of the unit cell is indicate the AA stacking. Along the diagonal, we have a different stackings, like AA stacking. Here is a 1/3. We are indicate the BA prime stacking, and 2/3 is 2/3 AB prime stacking. We have different stacking. Based on this one, we are going to calculate the local density of state around the AA region. Here we are going to the same angle, like 5 degrees. This is the local density of states. We are found the MO orbital around the like 5 degrees built from AA stacking. Here we are observing the different orbitals in the MO orbital, like dz squared, dxy, dyz. All among these orbitals, we get the sharp peaks in the dz square. That means this main contribution of these local density of states in the d0 orbitals. Remaining orbitals also we have a small contribution. So these all the calculation, we are applying the Gauss-Bodian standard deviation at sigma equal 2 million electron volts. So this is the same phenomena we are applying the smallest angles like this. Smallest angle confined state in the A region in the Mori pattern. So the smallest angle we can observe here, but here we represent the band dispersions and local density of states for dz square orbital of MO atoms. Okay, this is built from AA stacking. Here we are getting the largest peak, the sharp peaks in the A region. How we are getting this one? Because of these because of these electronic states in the flat isolated bands are more related, more localized in the A stacking region. That's why we got the sharp peak region. But in the ABA region and ABB region, we didn't get any of these localized states. That's why we didn't get the sharp peaks here around the region. We got the small regions here, and also we have here this in the conduction band. We have here 2 quasi-fold degenerate bands, and this is a 4-fold degenerated bands. And in the valency band, we have non-degenerated band. Here is a 2-fold degenerated, quasi-degenerated bands. Here we can get this one. So we are going to find the weights of the eigenstate in the real space of these bands, conduction and valency bands of this one. So if we are showing this one, average weight of the eigenstates along the real space, there is a gamma, K and M points in the symmetry points. You can observe this one is indicate the four-fold quasi-degenerate in the conduction band. Conduction band, we have the energy range 1.682 plus 0.02. It's on and plus or minus. And this is a two-fold quasi-degenerate in the conduction band. Okay, this is a conduction band. So here we can, this one is a non-degenerate band in the valency band, highest valency band. This one is a two-fold quasi-degenerate. You can observe it in the, this is an empty space around the, but the local density states is happening around the region. Here is a non like a valency highest band. We can occur the highest peaks, and because of that, because of this one here, we get the highest peaks here. And this one is done, this one non-degenerate case. So here is my conclusion. We have revisited in the tight banding description for the twisted bilayer. Many people have done in the monolayer case, and this is normal. And we are going to, we found that it's a good agreement, twisted bilayer MOS2. It's a good agreement with the highest valency band regions, both cases for the all angles. And we found that isolated band appear in the valency and conduction band close to the 5 to 60 degrees. After 2 degrees, the valencies are vanishes, and depending on this band, this real space confinement occurs around the center of the A region, also in the ring around the center of the A region. We also checked for the, we checked the twisted bilayer MOS2 built from AB stacking under different TV models. This one also we got the qualitatively same behavior. So based on this one, based on this work, we strongly recommended that this is a very good candidate for the studying the correlation effects and the quantum transport properties of the twisted bilayer MOS. Yes, Penny. Thank you.
Thank you very much, Venki, also for staying on time. So we would have time for 1 or 2 questions at least. So, any volunteers? Yes, Rudolf.
So experimentally, how do people do the twist? Can you do the twist?
Yes, Professor. Many experimentally, people are already done with the twisted bilayer graphene, and these people also done in one of the Nature publication is.
But you just grow it and you get it at one particular twist angle, right? There's nothing where you can continuously change it.
Yes, particular angle for the first, they may be first the one layer keep it, and another one is they made it, another angle they made it second time like this. They couldn't twist like this.
Okay.
Okay, thank you. We have 1 more minute for 1 more question. Since that doesn't seem to be the case, let's use that to stay on time with the next talk. So the next talk is Arpit Arora, who will talk about cooperative orbital moments and edge magnetoresistance in monolayer tungsten telluride. So we need the, yes, here it is. Maybe we can have a video. It might be a bit nicer, if you don't mind.
Sure. Can you see my video?
I don't see it. Yes, now I see it. Perfect. You're ready to go.
Okay, just a second now.
If you reshare.
Yeah, I stopped sharing so that I can. Okay, so now you can see my screen and my video, right?
Yeah, it's perfect for me.
Okay, so hi everyone. I'll be talking about cooperative orbital moments and edge magnetotransport in monolayer tungsten telluride. So let me just give you a brief overview what I'll be talking about in the next 10-15 minutes. Most importantly, we see a vanishing gap in the edge spectrum at some critical orientation of the magnetic field, which arises due to the cooperative orbital magnetic moments. And the consequences are seen in the edge magnetoresistance, which almost vanishes at the same critical angle where the gap is vanishing. So with this, let me walk through the outline of the talk. First, I'll talk about the quantum spin Hall effect and the fate of the edge electrons in a magnetic field. To understand the effects in tungsten telluride, I'll talk about crystal and band structure, and then I'll finally discuss the cooperative and ordinary edge magnetoresponse. So quantum spin Hall effect is the counterpropagation of electrons in helical edge channels, which arises due to the topological band inversion in two-dimensional topological insulators. These are characterized by quantized conductance, and the electrons are governed by a gapless dispersion where the Dirac point is protected by time reversal symmetry. Now we can break this time reversal symmetry by applying a magnetic field. So what happens is that a gap opens up in the edge spectrum, and it can be seen in experiments as magnetoresistance. So I show this data in this figure, which is with reference to the classical example of mercury telluride quantum wells. So what we see is that if we apply an in-plane magnetic field, the resistance, the conductance fall by a small amount. That is, we have a small magnetoresistance, and for a perpendicular magnetic field, we see a drastic fall. If we see a drastic fall in the conductance, that is, we have a very, very large magnetoresistance. So let's try to understand this anisotropy. And this can be done by considering the effect of magnetic field on the electrons. So electrons interact with the magnetic field via Zeeman interaction. That's a spin degrees of freedom. And secondly, the magnetic field also alters the orbital motion of the electron. So let's try to figure out what happens to the edge spectrum, whether a gap opens or not when we apply the magnetic field in various directions. So when we apply a magnetic field in X direction, the gap opens up, a Zeeman gap opens up, and a gap will not open up by the orbital contribution because in a two-dimensional material and an in-plane magnetic field, the field lines will just pass through without affecting the sample much. And by the same reasons, we see similar effects if we apply a magnetic field in Y direction. Now, if we apply a perpendicular magnetic field, that's a magnetic field in Z direction, we find that there is no gap opening either by the spin contribution or the orbital contribution. But this does not explain what we just saw in the previous slide. So this can be explained if we consider a particular feature, that the bulk inversion asymmetry of the zinc blend structures, which belongs to the mercury telluride quantum wells. This bulk inversion asymmetry is taken care by a zeroth order type Rashba spin orbit coupling, which couples the opposite spins. So the coupling of opposite spins leads to an opening of a gap in the edge spectrum on application of a perpendicular magnetic field, and it is found that this gap opening is actually 50 times larger than the in-plane counterpart. So to review what we just saw is that if we have an inversion symmetric crystal, there'll be no gap opening due to a perpendicular magnetic field. Whereas if we break the inversion symmetry, there will be a gap in the edge spectrum, which comes from the orbital contribution and goes as 1 over m squared, where m is the half of the magnitude of the topological band inversion, and in case of mercury telluride, this is 10 MeV. Now with this, let's try to infer what we'll have in the case of tungsten telluride. Now in tungsten telluride, which has a topological band inversion of 1 eV, so the half of it is 500 MeV, so we expect that this orbital gap must be suppressed by a factor of 2500. So which means that we have a vanishing gap for the out of plane magnetic field, and the in plane gap actually overwhelms the out of plane counterpart. But what we see is that there's actually some critical orientation of the magnetic field where we see a vanishing gap, and it neither belongs to the out of plane, neither it belongs to the in plane. So now let's try to explain this, and for this we need to know how tungsten telluride works. So tungsten telluride has these buckled tungsten and tellurium atoms, which are arranged so much so that the crystal obeys 3 symmetries: the screw symmetry, which is this zigzag line, and we have a mirror symmetry, which is this yellow line associated with a half a translation in the unit cell, and we also have an inversion center. Now, these symmetries give rise to a tilted BHZ model near the gamma point, and we have this momentum-dependent mass which takes care of this topological band inversion, and we have these anisotropic Dirac velocities. Now, to complete the picture, there is something special happening, and the special thing is that we have these tellurium atoms displaced from, they're misaligned, they're displaced from their position. This gives rise to a effective dipole moment which has in-plane and an out-of-plane component. Now this out-of-plane component of the dipole moment is something usual, and it's the same thing that's responsible for bulk inversion asymmetry in mercury telluride quantum bells, and rightly so, it's governed by these zeroth order Rushbar terms which couple the opposite spins in the opposite bands. But this in-plane dipole moment is actually something unusual and gives rise to Ising type spin orbit coupling, which couples the same spins but in opposite bands. Now, if we have these two spin orbit couplings at the same time, what we see is cooperative orbital moments coming to the picture. Now, when I talk about orbital moments, I say again, I'm particularly concerned about the out-of-plane response to the magnetic field. So this is given by these three terms, and we note that the first term, this GZZ, is nothing but the Zeeman interaction term, and we have these two terms, GXZ and GYZ. Now first let's have a look at GYZ. Now this GYZ is the ordinary orbital magnetoresponse, which I earlier showed you in mercury telluride quantum bells, and as I said before, this goes as 1 over m squared. And correctly, as we suspected earlier, this is fairly suppressed. Now we also have this GXZ, which is actually the cooperative orbital magnetoresponse and requires non-zero Rushbar and spin orbit coupling, and it goes as 1 over m instead of 1 over m squared. And most importantly, this overwhelms GYZ by a factor of approximately 250. So with this, along with the in-plane response, which is just given by the Zeeman terms, this GXX and GYY, and these gyromagnetic ratios are fixed around 2. And what we see is that we have this vanishing gap in the edge spectrum. So this, if you can see that this vanishing gap actually exists when the magnetic field is in the XZ plane, and this critical angle theta C is directly given by this GXZ. So if we say that GXZ is 0, this theta C will immediately shift to 0. That's the out of plane magnetic field. Now one more thing, that if we shift the plane of the magnetic field, that is if we move from XZ to YZ, we see that there is no longer a vanishing gap, but there still exists a critical angle, and this critical angle shifts to 90 degrees when the magnetic field is exactly in the YZ plane. Now let's try to understand this, and to understand this I present a small symmetry analysis so that the edge in consideration is this X edge, and we have this first term which describes the helical motion of the electrons, and we have the magnetic response. Now these Gij are the components of this gyromagnetic tensor, and we start by assuming that tungsten telluride has inversion symmetry. And the low energy tilted BHZ model that I presented allow us to model the inversion symmetry by the product of 3 mirror operations, that's MX, MY, and MZ. Now it should be noted that when we are along this edge, the X edge, Y going to minus Y is no longer a valid symmetry operation. So in this case, we just drop MY, and what we see is that in presence of inversion symmetry given by a mirror operation along X and Z direction, you just get the on diagonal terms, and these represent the Zeeman interaction. Now if we kill MZ, this is possible by the out of plane inversion symmetry breaking that can happen due to Rushbar spin orbit coupling. We see that we get this ordinary orbital response, which was also seen in mercury telluride quantum bells. Next, if we break MX, which is possible by the effect of Ising spin orbit coupling, we typically have, we have no symmetry, and we ideally allow all of these terms, and this GXZ is the cooperative orbital response. Now this has consequences, and these can be seen in the edge resistance, which we model by contact and channel resistance. And this channel resistance is calculated using Boltzmann approach under the relaxation time approximation, so much so that the scattering takes place through a short range scatterer. We see that there is this critical angle at which the channel resistance vanishes. And this can be seen by analyzing this curly L, which is the mean free path. And we note that the mean free path goes as inverse of the overlap of the counter propagating electrons. And if there is no gap opening, ideally we have no overlap, and the mean free path goes to infinity, and the electron can move quite freely. And I highlight two more features here. So where we plot the resistance at these two special points, theta C, where we have vanishing channel resistance, and theta max, we have maximum channel resistance. We see that the channel resistance at theta C is inert to temperature variations as well as the magnetic field, whereas the theta max is not only activated by temperature but also the magnitude of the magnetic field. With this, I would like to thank you all and leave you with the cooperative orbital magnetoresponse, which leads to a vanishing gap in the edge spectrum with respect to the orientation of the magnetic field. And at this critical orientation of the magnetic field, we see a robust vanishing channel resistance, which is inert to temperature as well as magnetic field variations. Thanks.
Okay, thank you very much. So also for the perfect timing, so that leaves time for questions. Any volunteers for questions? Well, if nobody else wants, I have a question that might be a bit tangential, but anyway. You know that in semiconductors, in classical semiconductors, you have a fractional quantum Hall effect if you include interactions. Is there something like a fractional spin quantum Hall effect if you include interactions? Have people thought about this?
We have not tried including the interactions, but what we suspect is that since it has this material has a large spin orbit coupling of 1 eV, we suspect that the interactions will not hold much into this because it's quite a big thing that we need to cover, and these plots already here are at the magnetic field of 6 to 12 Tesla, and so we require quite a big magnetic field so that we have these Landau level and interaction effects.
Okay, anybody had another question in the meantime? Yeah, Pinaki had a question. Pinaki, do you want to ask it?
Yeah, it's very similar to what Andreas asked. When you are talking about the edge states, that's a 1D channel, 1D
Yes.
Luttinger link,
Yes.
where any interaction will be infinite, essentially.
Sure. Yes. But again, this is helical. It's not exactly Luttinger liquid, but it's helical. We have two spins traveling at the same time, opposite to each other, and so I don't.
Two Luttinger liquids.
Okay. Yeah.
Right.
Sure. Two Luttinger liquids.
Have you thought of incorporating any interaction effects to see how they might affect what you calculate from non-interacting picture?
No, we haven't thought about this, but suspicion is that since the spin orbit coupling is too large, and actually these are, although edge channels, they are 1D helical edge channels, but they somehow depend on the bulk, and we just see this capital M, which is the magnitude of topological band inversion, and so we definitely have bulk which has a strong role to play. So I think interactions will still not play a good role because these magnetic fields are already too large. These go from 6 to 12 Tesla, and we still find very convincing Landau levels. So I don't think we have anything interactions.
Okay. Okay, thank you. I didn't see any further questions. Last chance. Otherwise, let's try to stay on time and move on to the next talk. So thank you very much again. And now the next speaker goes back to France. It's Ahmed Missaoui. If he can share his screen, then he is scheduled to talk about electronic properties in bilayer graphene monitored by selective functionalization. Ahmed, maybe presentation mode. Well, you seem to have a technical... Let's see your screen. Okay.
You see my screen?
I see a screen. It's not in presentation mode. Do you want to try to? No, it's not. I see your Zoom window. That looks good. Oh, looked good.
Okay. You see my screen now? It's okay?
Now it's okay. You go.
Okay, thank you, Andreas. Today I present some results in electronic properties in bilayer graphene monitored by selective functionalization. This work is done in MPTM laboratory in collaboration with the University of Tunis and University of Grenoble. In outline, I start by a short introduction for electronic structure of graphene monolayer and graphene bilayer. Then I present some results for graphene bilayer with adsorbate. And after I show you the effect of rotation of a small rotation between the layers. Graphene, it's a one layer, it's one 2D materials. So the atom carbons in graphene are characterized by sp2 hybridization and Nida-Bay arrangement. In real space, the lattice is hexagonal with the two atoms per cell, A and B. In Brillouin zone, in reciprocal lattice, the Brillouin zone are delimited by 3 bonds, gamma and key bonds. For bond structure, we use the banding model with two approximations. We take count only pz orbital and the coupling between first neighbor only. The Hamilton is given by this formula. Around the key point, the dispersion is linear in form Kiran-Drake cone. The density of state presents the electron hole symmetry around the energy Dirac here at 0. Now, if we try again, we find using graphene bilayer. We have two types of stacking, E stacking and E stacking. The two layers are separated by distance d around 3 angstrom. In this work, we are interested only for AB stacking. For the system, the unit cell has 4 atoms, E1, B1 in the first layer and E2, B2 in the second layer with two parameter coupling. The band structure around the key point is parabolic, and this system presents properties different from those the monolayer. In this work, we will study the effect of adsorbate in this system. To adsorbate, the study creates the band on surface by a sample covalent band, like hydrogen atoms or CH3 molecules. The pz of this atom will be occupied by this banding. So the sample modeling is to remove the pz of of this atom of carbon, and we consider him like a vacancy. In our case, vacancy or adsorbate is the same. For transport, we use the Q-Gromwood formalism, where the conductivity as a function of velocity operator. For zero vacancy, this conductivity is given by Einstein formula as a function of density of the state and diffusivity. Numerically, use the recursion method to calculate the density of state, and the recursion method to place a Chebyshev polynomial to calculate the diffusivity. With this method, we can take into account the elastic scattering in very large supercell, and also inelastic scattering by the relaxation time approximation. In this structure of graphene, the atom E and are not equivalent. The atom E, for example, here has 3 covalent bonds, and the atom B has only 3 bonds in the graphene. So to create vacancy, we have many possibilities. In this work, we are interested only for 2 types of vacancy. First, E1, E2 vacancy, or B1, B2 vacancy. So I started by E1, E2 vacancy. The first plot is the total density of a state as a function of energy for different concentration. The dashed line here is density of state without vacancy. So we can observe the 3 different regimes. At zero energy, here we have mid-gap state. These states are coming from the presence of defects in the structure. But when the defects are localized in the same sublattice, we can remove the peak for this mid-gap state. Around the Dirac energy here, we have a gap, and the bandwidth of this gap depended on the concentration of vacancy. Also, we find this gap in microscopic conductivity. Here, we find this gap. And so far from Dirac here, the conductivity decreases when the concentration of adsorbate increases. This is a typical behavior of Boltzmann. Now we will study the second type of vacancy, B1, B2. This we are interested on this 2 types of vacancy, B1 and B2. For this type, we are interested in microscopic conductivity shown in the main plot here as a function of energy for different concentrations. The concentration of 25% and 30%. So also far from the energy, we found also the Boltzmann behavior quantity increase when the concentration of vacancy is. This behavior corresponds to in the density of a state here, when the density are weakly affected by vacancy. Now around the energy Dirac here, the microscopic conductivity is independent of concentration and energy. So we call this plateau of conductivity. We find this behavior in the monolayer graphene with adsorbate randomly distributed between the 2 sublattices A and B. We find this minimum of conductivity is monolayer behavior. Now, at energy of coupling between the 2 layers, we find a spectacular behavior here. The 2 peaks in the both sides. The conductivity here increases when the concentration of adsorbate increases. It's a very spectacular behavior, and all this states are separated from from the spectrum by a gap here. Now we studied the effect of small rotation between the layers. The origin of the angle is stacking when the atoms of the two layers are one below the other. Here we started by stacking, and for small rotation, for example, in this case, the angle is 60 degrees. We found in the structure a Murray partner with a different region in the structure. We have three regions here. For example, we have E region, and we have EB and B region. The E region is more interested because all the states of the system are localized in this region. In this work, we study the effect of a sorbate randomly distributed in both layers first and in just in one layer. Here, the conductivity in this plot are shown for three concentrations: 0, 5, 1, and 2%. The full line is vacancy into distributed in layer 2 in one layer, and the dashed line vacancy are distributed in both layers, in two layers. For this angle, we find a plateau of conductivity here for high concentration bigger than 1%. And we find this plateau for all the angle. If we see here, donc it's a microscopic conductivity function of angle square for an energy minus 0. electron volt here, 0 electron volt here, and 0.1 electron volt here. In dashed line, we see the conductivity present a plateau of conductivity. The conductivity is constant and independent on angle. So with the vacancy distributed in one layer, the conductivity increases when the angle increases, like this. And this we can explain this because when the angle increases, the two planes are more and more decoupled, and for this reason the conductivity increases with theta increases. In conclusion, we have studied numerically the effects of adsorbate and graphene banded structure, vernal bilayer and twisted bilayer. In vernal bilayer AB, from in presence of adsorbate, far from the energy, which regime is reported, and in intermediate regime around the energy of Dirac, we find the gap with E1, E2 vacancy, and the isolated band of localized states with B1, B2 vacancies. In twisted bilayer, we have shown that the conductivity is independent of the angle in the presence of random vacancy, and when the vacancy are in one layer, the conductivity increases linearly with the angle. Thank you for the attention.
Thank you very much, Ahmed, also for respecting the time. Unfortunately, we had some audio problems, but I hope it came still across. Other questions? Any volunteers? Okay, then let me ask one question. I'm not sure whether I missed that and you said it. So in particular, if you put vacancy selectively into one plane, you might wonder how you do this in practice. So what do you have in mind when you talk about vacancies?
in twisted graphene?
Well, at the end, you said, yeah, in one layer. You only put them in one layer. How do you do this?
Yeah. Yeah, we input the vacancy in one layer. For example, it's vacancy random distributed between two atoms in one layer. We remove the atoms in the structure. In the Hermitian, we remove the atoms.
Well, okay, thank you. Unfortunately, we still have sound problems. Are there any other volunteers for questions? If not, then I suggest that we thank Ahmed and move on to the next talk, which means moving further west. Next speaker is Oleg Zaboronski, and he will switch gears and talk about dualities and representations of Hecke algebras for interacting particle systems. So let's see whether he is there. Yeah, I see him. And now, Oleg, can you share your presentation?
Yeah, I'm trying. Okay, can you? Okay.
We have sound. Okay, and this is again a 20 minutes presentation, including discussion time. Here you go.
Okay, thank you very much. Thank you, Andreas. So let me see, is it in full screen?
Not yet.
Okay. Oh. Okay, so it will be indeed quite a change from this hardcore solid state physics presentations, but I will try to emphasize possible connection points. Of course, I'm going to talk about something which can be solved exactly, meaning that these models might seem trivial to many of you. Okay, so my collaborators, Roger Tribe and Bruce Westbury. Roger is a probability theorist and Bruce is an algebraist, both from Warwick. Okay, so, and given that there is such a wide range of topics covered in this conference, I will spend most of the time doing the introduction. And the idea goes back to Marian Smoluchowski, who decided to use the ideas of kinetic theory to study the kinetics of chemical reactions. And what are the simplest models? Well, you can take a very simple single species annihilation, meaning that you have one type of particles moving around according to some law, and when they bump to each other, they immediately disappear from the system. Or if you would like to modify this a little bit, it's a coalescence reaction when upon bumping, particles fight and only one survives. So that's a coalescence. So, and these are the simplest models, and interestingly enough, even though I don't really know much about it, some experimental realizations of a mixed system where both annihilations and coalescences are possible was realized in nanowires. So now let me try to do what Smoluchowski has done. So at a very, very simple level. So imagine that you are interested in the density of reactants. So clearly particles keep coalescing or killing each other completely, and the density is going to zero with time. Can we decide about the law of decay? Well, this is roughly what Smoluchowski has done. So let us look at the rate of change of the density of reactants. in principle, so particles keep bumping into each other, and presumably the more pairs you have within the interaction volume, the more reactions will take place per second, say, at a given temperature. Therefore, it is reasonable to estimate the reaction, to say that the reaction rate is proportional to the number of reacting pairs. So therefore, we've got to have the square of concentration on the right-hand side, and then the dependence on the reaction radius, the velocities of your particles, it all goes into the reaction rate. So this is the simplest rate equation, which tells us that rho dot is proportional to rho squared, and the coefficient of proportionality is negative. So we have an ordinary differential equation, and it is quite easy to see that its solution at large times is 1 over time. Indeed, 1 over time squared, 1 over time derivative is 1 over t squared, 1 over time squared is also 1 over t squared, everything matches. So this is the large T asymptotic of the solution. Okay, so now notice that we have made an implicit mean field assumptions. Namely, when we estimated the rate at which particles collide, we presume that when particles bump into each other, they are completely uncorrelated. Okay, that's why the number of pairs is estimated by the total number of particles squared. Okay, so therefore, if we are using the non-correlatedness assumption, we should say that if we have particles that enjoy disjoint positions, they don't know about each other, so the probability of finding them should be just the nth power of the probability of finding a single particle at a prescribed position, which is proportional to density. Perfect. So we conclude that the n-point correlation function should decay as t to the power minus n. Okay, so now I would like to say that these formulas are completely wrong in one dimension. So they bear absolutely no relation to reality. So, and in order to do that, in order to convince you of that, I need to formulate the model a bit more precisely. So, and I will start with specifying the way in which particles move about. Okay, let's say that we are trying to model some kind of diffusive motion, and I will say that particles perform independent, continuous time random walks on a one-dimensional lattice until they meet, and when they meet, they just disappear in a puff of smoke. Okay, so, and the main object I'm going to be interested in is the probability of finding particles at positions x1 to xn on the lattice at the moment of time t. Okay, so these are multi-point correlation functions, and they completely, if you know all of them, you know the distribution of all particles in your system. Okay, so, and you can take the continuous diffusive limit of your system, in which case you will end up with annihilating Brownian motions, and as stated, the model is referred to as annihilating random walks. Okay, so I'm forgetting about coalescence for a second and talking about annihilations. So this model has a long history, starting from 1907. It's not really important to read through this list. What's interesting is that for about 60, 70 years, the model has been studied by physicists and mathematicians fairly independently. And only recently more interaction has started. So many of you, of course, recognize the model for annihilating random walks. So all you have to do is to consider the Glauber spin chain. So it's just kinetic Ising model, and rewrite everything in terms of domain walls. And domain walls will behave like annihilating random walks. So it's a well-familiar model to many of you. Now, what are the results? So Smoluchowski predicted that, say, the concentration of particles in this model will decay as 1 over time. Okay, so, and that prediction dates back to 1907. Now, in the 80s, it was realized, and actually you can already deduce these results from Glauber, that the actual decay law of the concentration is 1 over the square root of t, so it's much slower. Okay, and what about endpoint functions? Endpoint functions decay in an even more interesting way. So you have, it decays faster than the nth power of the one-point function. So there is this contribution, which many of you would call anomalous dimension by analogy with localization theory. So this density decays, the endpoint function decays faster than the nth power of the one-point function due to the anti-correlation, the effective repulsion which is developed in the system. In other words, this shows to you that the assumption of mean field theory that there are no correlations is completely wrong. And in the 90s, it has been shown rigorously that if you are in dimensions strictly greater than 2, say you are on a 3-dimensional lattice, then the one-point function does indeed decay as 1 over time, according to mean field theory, and the dimension 2 is critical. So the one-point function behaves as 1 over t, but there is a logarithmic correction, log t. Okay, and the endpoint function, and this is a fairly recent result for a 2-dimensional system, also exhibits the anomalous dimension. Look, there is this quadratic dependence of the logarithmic correction, of the exponent in the logarithmic correction on the order of the correlation function. And I would like to try and understand how to start deriving formulas like this one, how to analyze this model in 1 dimension, and how to go beyond mean field theory. Okay, so I am talking about a very simple model. So the configuration space, so I have my lattice, and each lattice side can be either empty, corresponding to 0, or has a particle on it that corresponds to 1. So this is my state space. Okay, so, and eta is my state variable. If eta x is equal to 1, then there is a particle at side x, and if eta of x is equal to 0, then side x is empty. And in probability theory, we define our model using generators, and the generator basically tells you this: if you want to take the expectation value of some function of your random configuration, then the result is the same as the application of a certain linear operator to this function under the sign of the expectation value. And this is called a generator. So in principle, it is conjugated to the Fokker-Planck operator, which some of you might be more used to. And the generator for this model for annihilating random walks can always be written in the following form. So it's the sum of the lattice sides, some matrix, which I refer to as sigma minus I. And sigma is actually can be represented as a 4x4 matrix. Why? The configuration space of 2 lattice sides can be either 0, 0, 0, 1, 1, 0, 1, 1. Okay, so the dimensionality of the space of functions on 2 sides is 4-dimensional. So I can represent the action of a linear operator on the space by a 4x4 matrix. And this 4x4 matrix is extremely simple. So the states are enumerated as follows: 1, 1, 1, 0, 0, 1, 0, 0. Okay, so here we go from 1, 0 to 0, 1 with rate 1. That's a random hop. This element corresponds to the random hop to the left, and the only remaining non-trivial element is here. We go from the state 1, 1 to 0, 0. This is annihilation at rate 1, because you can annihilate a pair by hopping to the left or to the right. Now, if I use this careful definition of the model and try to calculate the rate at which the one-point function, the density of particle changes, I will find the two-point function on the right-hand side. And this is the non-closure problem. And there is one important point, and many of you definitely know this. So if you take this, if you now try to write down an equation for the two-point function by taking the time derivative of this non-closed term, you will get an equation with a three-point function in the right-hand side, and so on. So you get an infinite system of equations, now which is known to some of you as a Hopf chain. What would happen if you try to truncate this system of equations at any finite level? You will never get the correct exponent. All you will get is a certain expansion around the mean field value of the form 1 over t plus a bunch of logarithmic corrections. In other words, in order to go from, say, 1 over t to 1 over root t, you need to find this infinite system. And this is always the case when you are dealing with strongly correlated or strongly coupled systems. No truncation will help you. So how can we work? So what can we do in this situation? It turns out that we are saved by algebra. So you see this, so we have our generator given by the sum of two-side generators, which are represented by these 4x4 matrices. And I can try to find the algebra of these matrices. Well, if the distance between lattice sides on which these matrices act is, say, greater than 1, then these matrices just commute. So they act on different arguments of the test function. So then you look what happens at a single side, and you find that this matrix is idempotent. Its square is equal to the matrix itself. This is called the Honecker relation. Then you try to see what happens to the neighboring generators. And they create this, so they obey this complicated relation. But it only looks complicated. If you forget about this linear term, then you will find this quite famous relation which many of you have seen in the braid group. So amazingly, for annihilating random walks, the generators obey the relations of the Honecker algebra. So all these relations together means that sigmas generate the Honecker algebra. And I'm going to finish with just a single claim. So that if you take any continuous time Markov chain, so in one dimension, with the generator of the form the sum of two particle generators minus this term needed for the conservation of probability, and assume that sigmas generate Honecker algebra, then you will find only 4 models. You will have mixed coalescing annihilating random walks, and this is basically how the domain walls in Potts model behave. You will have annihilating random walks with pairwise immigration, and this is just a kinetic Glauber chain with positive temperature. Coalescing branching random walks, this is what you have in the so-called Brownian web, or the symmetric exclusion process. And even though it is impossible for me to explain how to use this fact that of Honecker algebra, I claim that studying representations of Honecker algebra, you can linearize the model and solve the non-closure problem. And all these models will have multi-particle correlations presented on this slide. Okay, so, and this is basically all I wanted to say. And I didn't explain it properly, but you have to believe me that this Honecker symmetry can be used to effectively linearize all of the models. Okay, and by the way, all the models which I listed are these quite standard reaction diffusion models which have been in consideration for quite a long time. What is also surprising is that the answers which you get are of interest to non-Hermitian random matrices like Geneva matrix model, and they can also tell you something about the distribution of zeros of random functions like random Katz polynomials. And finally, this is an example of integrable models in the sense of quantum integrable systems, because it is known that starting from Hecke generators, you can build solutions to Young-Maxter equations named the R matrices. And that's it from me. I hope I didn't overrun. Thank you very much.
Well, thank you very much, Oleg. Perfect, including timing. Now we have time for questions. There were already two in the chat, and let's start with Christian.
Yes, I had a very simple question. Okay, yes. I don't understand how you can calculate, endpoint correlation functions when particles are annihilating, because the order n would change.
Yes.
So I'm lost here.
Okay, thank you very much for your question. Okay, so this is exactly what I couldn't explain, but you know what? Let me not use this slide. Okay, so let me explain it in a much simpler way. So just to stick to the conclusion of the algebraic analysis. So I will change observables. So I will look at the probability that the number of particles, say, in a certain interval is even, right? Mm-hmm. So now, if you look at annihilations inside mm-hmm. the interval, it doesn't change the parity of the number of particles, right?
Yes.
The parity can only change if you hop over the boundaries, into the interval or out of the intervals. This process is pure diffusion. It doesn't know anything about interaction. Therefore, if you write down equations for this probability, it will be a linear equation. It will be just a heat equation.
Okay.
So you can solve it. Now, if you take, and that will give you the one-point function. Essentially, it's very close to how Glauber could have computed the one-point function had he been interested in it. Now, look at the probability of finding an even number of particles in a union of intervals. Exactly for the same reason, this probability solves a multidimensional heat equation. And then the boundary condition is that when you take the size of any of these intervals to 0, you will get exactly the same probability, but for the smaller number of intervals.
Okay.
That means that you have an upper triangular system of equations, which allows you where the endpoint function enters as a boundary condition for the equation for the n+1 point function. And that's how you can solve them all. That's how you solve this non-closedness problem.
Okay, I see. Okay, thank you.
Thank you for giving me 5 more minutes to talk.
Oh, there are more questions, and since Rudolf is asking too many, Pinaki goes next. Pinaki, do you want to ask a question?
Yes, I have a very simple question. Where does Arrhenius equation fit in in this framework?
So could you please explain me what this equation is?
Arrhenius equation is the chemical kinetic reaction, rate of chemical kinetic reaction. I think it.
Oh, very good. Okay. Okay, so it's basically this, usually it's e to the power minus beta energy gives you the reaction rate. Okay, so imagine that we're a Smoluchowski again, right? And of course, Smoluchowski is trying to understand the rate at which particles react when they bump into each other. This is where you start using Arrhenius law in order to find the answer for the coupling constant.
I see.
Right? But the fun thing is that if you are in one dimension, this carefully calculated reaction rate doesn't enter the final answer. Because due to the strong interactions, it gets renormalized away completely. And the answer is actually universal, and it doesn't depend on the bare interaction rate.
Okay. Okay, thank you.
My pleasure.
Okay, well, Rudolf now gets his say, but maybe you can keep it in 1 minute, Rudolf.
Yeah, just a quick question for your claim. Do you have some physical interpretation? So what is underlying all this? I mean, for integrable systems, I know it's integrability, conserved quantities. Do you have an idea what underlies?
Yes. Yeah. Okay. So that's another fantastic question about the slide which I missed. So if you have Hecke algebras, these algebras have a large center. In other words, you can find a lot of operators which commute with the generator. And this is the link to integrable models in a more traditional sense.
Okay, thank you.
Okay, are there other questions? If not, then it's maybe the right time to open the microphones and give a round. So let's see.